Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today we're going to continue the series with the collaboration for the JAT amplifier, the John Audio Tech amplifier, right? So what we're doing, we're designing the power supply that's going to have a plus minus voltage rail, and it's going to come off of your AC power. So we're going to first condition that power, kind of smooth it off, and kind of bring them clean as we can with the power factor correction circuit. So today we're going to pick out several of the most important parts of that circuit. Okay, last video we looked at the inductor and how to size it, and we're going to talk about that just a little bit more. Okay, had some good questions, and we're going to kind of fill in some of those questions. Okay, so keep your questions coming. Ask, whatever you don't understand, go ahead and feel free to ask questions, because we want to make sure we cover all the bases. And I forget to fill in all the bases sometimes until you guys ask questions, and I go, oh yeah, that's a good question. So, all right, so let's start with looking at our circuit. All right, so here's our circuit. Maybe we ought to zoom in on this a little bit so you can see a little better. All right, so we have this input circuit, bridge rectifier, so on, maybe some filtering, and it's going to provide us this pulsating DC, this blue waveform, right? And that's it. Here in the States, that'll be 60 hertz, but it'll look like 120 hertz because we've taken the negative pulse and flipped it up to the top. So we get 2 pulses for every cycle, okay? Then what we want to do, the red is a current, and then we're going to pull current. We're going to pulse this thing, so we're taking a little bit of current, in slices all the way along. So we're taking current throughout the pulse width. That's why we can get that great power factor. So it keeps basically the current in phase with the voltage. All right, so here's the 3 things we're going to choose today's video, these 3 parts. Okay, the first one, the controller. Now the controller, we want a continuous conduction mode, right, where the inductor never discharges fully. If it does, and then it waits for the next pulse to start again, that's discontinuous mode. If it just touches, and as soon as it touches, you start another cycle, that's where the frequency has to change to allow that to happen, and that's a critical conduction mode. That's one of the names for it. We want the continuous conduction mode. That's usually better for higher power. And even though this controller, yeah, I'd say this is getting to the point where it's becoming kind of necessary, I think. Otherwise you get these huge ripple currents because you're going from here all the way up to here. Okay, so there's what our current's going to look like. And since we're taking currents in little chunks all the way along the voltage waveform, it keeps the current and the voltage in phase. So great power factor, right? So that's how we correct that power factor from the bridge rectifier and a big bolt cap. Instead we have a small cap here, so this guy can boost current into the bolt cap over here. So let's go ahead and choose this. We want continuous conduction mode. I think 125 kilohertz in this case. When you go higher power, with high voltage, usually you don't want to switch too fast. But in this case, I think 125K is going to be nice. It'll keep the inductor smaller, help keep the capacitor smaller. So continuous conduction mode with something we can go 125K, right around that neighborhood. The other thing, we want to drive the FET directly. We don't want to drive chip or some other way to drive the FET. So we want a controller that has that. I've looked at a lot of these controllers over time, so I kind of know how to zero in on them, or which ones do that. I don't know them all, but I do know a fair number of them and which ones do what. So let's go choose that controller. All right, guys, here we are at Mouser. Let's type in PFC controller. And it says isolated DC-DC. We don't want isolated converters. This is non-isolated. There we go, PFC. Okay. And, all right. I was looking to see if I can search for constant conduction mode, but doesn't look like it. Wow. Okay, so just looking down here through stock, here's this fan part. It's a through-hole part, but there's 12,000 of them. Texas Instruments. Now, here's this Infineon part. Look at that, 19,000. That's a lot. I'm somewhat familiar with this Infineon part. So let's go ahead and click on this guy. This data sheet. Well, here, scroll across here. Look at all the columns. Okay, it's SOIC-8 is a package. The SOIC 8. Switching frequency 70 kilohertz on this one. Let's see what else we have. I think that one has, you know what I'm going to do, this Renaissance part I'm familiar with too. I've used that part. But you know what, kind of interested in using this Infineon part. So I've done some searches not too long ago, and the parts I like to use normally, the Texas Instruments, the one from Renaissance, they don't have much stock. The Renaissance isn't too bad, but this Infineon is also a great chip. And here, let's apply the filter. We got 19 of those. Let me know if you guys have one that you like, that you think might be a better option. But look, there's 5,000 of this one. Yeah, that Infineon part, I'm not really familiar with that one. There's 5,000, but I think the reason why, it's probably not the conduction mode we want. And unfortunately, they don't show them here as a category. But right here, this one's variable frequency adjustable. I mean, we can select the frequency. So I kind of like this one. The other thing, you know, I've done a lot of searching for these kind of parts, and let me see, the one, I think these two guys both have adjustable frequencies. Look, there's 21,000 of this one. So let's take a look at the data sheet of this one. All right. One of the things I've, you know, looking at these things in the past, I kind of know how to zero in on which ones I want, because I know which ones have this. Well, at least I'm familiar with the ones that do have this CCM, the continuous, and also that have enough drive capability that can drive a FET. And usually you want something that can drive 1 to 2 amps. And all right, guys, this is the PDF I just exported, and look at this. It's pretty recent chip, pretty recent version, 1.3 2019, so that's pretty cool. Here we are, previous versions, 1.2. But yeah, here we go. Here's some of the major highlights, I guess, the features. It's nice to read the description. And there's the part right there. That looks good. And coming down here, it has, you know, you can read the description in each pin. The thing I'm kind of looking for is frequencies. We can adjust it between 20K and 250K. Oh, here we go. And the gate, it's capable of 1.5 to 2 amps. I kind of knew that. I know these ICE chips have some nice drive, as well as some of the other chips I've used in the past. So that's why I was kind of zeroing in on this Infineon line, because I know they had high quantities available. You know, I've done searches in my job. All right, I just want to rotate this picture so you could see it. Here's the power AC coming in. There's our inductor, our FET, and there's our SiC diode. That's what we want to choose. And this diode right here that wraps around kind of helps charge this cap until stuff gets going here. Our input capacitor, which will be small ceramic, and our bulk capacitor C2, which will be kind of big, and our feedback. So it kind of shows the connections to our circuit, which these chips are somewhat common in that sense. They have kind of the same functionality in that. Maybe some might say they do it better or whatever, but of the chips I've been looking for, they're pretty similar. And here's the current loop block, the voltage loop block, protection over voltage, over current, that kind of stuff. Gate drive. Here's our pulse width modulation logic, our ramp generator, and here's a peak current right here. This guy's looking at the iSense peak current, and here's our frequency we can set up by placing a resistor here. So pretty simple. Compensation for the current loop, and over here we have compensation for the voltage loop, and there's our feedback right here, and our gate, VCC, and ground. So yeah, not too complicated. We're going to be very familiar with this chip. All right, so we'll go through a lot of this in days to come. All right, trying to keep the glare off the screen. So we got the controller chosen, right? So you know what? Let's go ahead and pick out the diode next, okay? I think that's a good one. Now the diode, I'm just showing a regular silicon diode here with the symbol, but really I think what we're going to do is use a Schottky, and a special type of Schottky for high voltage. Something that's rated around 600 volts, because we're going to have 400 volts over here, and when this pulls it down, it's got to block at least 400. So we'll pick, you know, a common voltage is like, say, 600 or 650. So there's lots of choices in that voltage range. And an important part, and the reason why we're going to go to a special diode, the Schottky, the silicon carbide type, another, you know, new semiconductor for the future, right? GaN is one, silicon carbide is another one. We're going to use silicon carbide so we can be cool. So anyway, the great reason to do that, other than just being cool and using something new, it's become kind of a common part for this application with continuous conduction mode. Why? When you pull this down and you have 400 volts here, you have a little bit of leakage current through here, especially, well, you will, especially with a silicon diode. With a Schottky, you don't so much. And for these high voltage, you really need a silicon carbide, okay? So it keeps the current from leaking through. It'll leak through every time this goes to zero. When you look at that as part of your equation, that turns into a fair amount of power dissipation. So what we'll do, like I say, use a Schottky, the silicon carbide Schottky, which won't allow that current to go through there. It does not have the reverse recovery that a silicon diode would have, where when it's forward biased, it takes a little bit of time for all those characters inside that material to separate again to open the voltage when the voltage is reversed, and they call that reverse recovery. There's a little leakage current during that time. So silicon carbide will solve that problem. Power dissipation then only becomes the current to the load multiplied by the voltage across the diode, the forward voltage. And these high voltage applications, it's usually over a volt. It's just something you have to deal with, and that's not too bad. We're doing 400 watts, and you know, we're going to have 400 volts out here, and we chose 400 volts because if we want this to be a universal input from the bridge rectifier, these peaks can go up as high as 264 volts AC, the high voltage, right? The peak of that is going to be in the 300 range, say 360. So we want to keep, we got to boost all the time, otherwise we're pausing and we're not boosting all the time. So we want to boost all the time to keep this current continuously flowing from one peak to the other peak all the way through. We don't want to go dead up here at the top either, okay? So that's why we have 400 volts out here. We could have chose 380, 390, but I just decided 400, okay? Makes the current out here a little bit lower. So, all right, let's go pick out that diode. All right, so here we are at Mouser.com. It's one of the vendors I like to use. So let's select a SiC diode. See, I've already done a search. Just type. All right, so let's type it in, SiC, and yeah. Okay, then down here, semiconductors and optos. So come here to Schottky diodes and rectifiers. Click on that. All right, so now we have this page. Let's come down here and let's look at quantities and sizes here. Now, the thing is, a lot of these guys are going to be
higher voltage, but let's just go ahead and make sure that that's what we're looking at. We want something like 600, 650 volts. Let's just go ahead and we'll select these, all three of those. Okay. Apply filters. We got 532 left. See that? So we've got down a little bit, but we still have a bunch. Now, if you know, now these are going to be the silicon carbide diodes, the SiC, right? So silicon carbide. And right here, I see some good candidates right here. 800, close to 800, another 800 in this package, and another 700 almost in this package right here. So it looks like that package might be a pretty good one. There's 200, there's 2,400 here. And let me see, which one is this? That's 4 amps. So forward current. Let's also choose something that is, let's also choose something that's more than 4 amps. I think we need, closer to 5 amps RMS. Let's just go to 6, get at least 6 amps, and we'll go all the way down here to the bottom 12. Well, it goes, let's go up to like 9 amps. So it's over the peak current that we have. And let's go down and select sheaves. I don't think, if we include too many, that's just too many to look at. So maybe we can even go to 30 amps. Okay, we'll just go down 30. That leaves us 274, so we cut it in half. But at least we are looking at what we want. Now, silicon carbide and silicon, these should all be silicon carbide Schottky diodes, I believe. So I'm coming over here looking. Okay, I'm going to scroll over here, and I can see the currents right here, forward current, and looks like all these have plenty. And if I look at these packages over here on the left, I've got this one from Little Fuse, this one down here from Little Fuse. There's, I guess, a 20 amp version, the 10 amp version. I could just go for the 10 amp version probably. And if I had to, I could go to a higher current value. Now, see this forward voltage? It's 1.5 volts with the lower current. So 10 amps might be the way to go. Let's just scroll down a little bit. See, we could use a through-hole part if we wanted, but I think we're going to stick with surface mount. So let's go to this 10 amp guy and just say, I think we're going to say we can do this one. Okay, so I'm going to open up the data sheet. All right, guys, so here's the data sheet for the Little Fuse Schottky diode. And this package here is pretty common, so we can find other alternatives for it if we need to. And look, PFC, it's made for PFC. And look, it's just a single diode in here, and it goes from pin 2 to the case, or pin 1. So I should say and pin 1. Okay, so that's how that connects. It can dissipate quite a bit of power. You can see up to 100 watts and 43 watts at 110. The forward current is 27 amps at 25C. So, and then I guess it drops to 12.5 amps at 135. We'll be operating somewhere in between there, probably in the, it's closer to 25 than 135, but we're good for 650 volts. So that's great. And forward voltages, here we are at 10 amps, 1.5. So we won't be drawing 10 amps, so we'll be less than that. Let's see if we have a curve down here. Here's the curve. So if we're drawing, say, 5 to, pulsing up around in here, we're going to be around 1.25 volts forward. And over here, reverse current, you can see it's very small. Here's a microamp right here. So very small currents. And this is 175C. So we'll be down in here. We'll be under a microamp. We should be under that. Yeah, here's your current derating for temperatures. And here's the capacitance, very small capacitance with the voltage. So yeah, this looks like a good diode. I think this one will work. Here's the physical size. All right. Yeah, so the package, it's a TO263, but a lot of us call it the D squared pack or D2 pack.
Okay guys, so now we're ready to pick out that third part for today's video, okay, the inductor. We came up with the value last video. It doesn't have to be that value. One of the things we're going to do in this is the inductance. Depending on the core material, you can have what you call a swinging inductor, where the inductance actually changes with current. And in an application like that, that's kind of nice to have. A toroid is often a good choice for that for a number of reasons. To keep the field close to the core, so you know it's self-shielded, but also for this swinging. You can get the kind of material that allows that inductance to shift over power, over current, a little bit easier. Okay, so we're gonna see if we can find something that will allow that. The reason why that's good is when we calculate the inductance, that's based on maximum load. But what happens when the load, which often it's going to be running not at maximum load? Well, in those cases, we're not going to need as much current. So this current in this inductor could dry up. It could be discontinuous. And there's a certain point where, you know, this current, once you're not pulling the load, you don't need much current. The inductor doesn't really have to be on, right? And so if you can make that inductor a larger value of inductance, it can kind of fill up with current and hold current a little bit longer. So so the swinging inductor is nice. We want more inductance at lighter loads, and we want the inductance we calculated to be at maximum load. So let's go see if we find that. Oh, here's another thing is that inductor, often if we're doing a custom inductor, and there are inductors out there, if we're lucky, find one with a second winding, and that's called an auxiliary winding, and it turns that inductor into kind of a transformer, right? But we use that winding to come up with the voltage to power this guy once it's up and running. That's kind of called a bootstrap voltage, but in this case, we're probably going to simplify things so that we don't have to you know, find the perfect inductor, because it might be hard to find that inductor. If you guys can find one, let us all know. Otherwise, we'll probably just come up with an auxiliary or a housekeeping voltage to supply voltages to our circuit that we're going to need. But anyway, just kind of throw that out there. Let's go choose that inductor.
Okay, here we are at Coilcraft. Coilcraft makes a lot of great inductors. It's kind of a go-to place. There's other vendors. Let me know what other vendors you like. I know there's vendors that make PFC chokes specifically. So let me know what you find there. But I just thought we'd come here since it's kind of a common, easy to find inductor place. And here's kind of the front page. A lot of stuff going on here. They've got a good website. Okay, let's go to power inductors right here. And as we come down, these are shielded inductors. We don't care about shielding for this thing. I'm kind of looking for a toroid, the donut shape inductor. They're self-shielded, so it's a good one to go with. And where are they? So here's unshielded inductors. I would think they'd be here, but I don't see them yet. Coupled inductors. Shielded, and here's some Class D inductors. That's pretty cool. Okay, I'm going to click on this unshielded right here. You know what I'm going to do? Let's just come up here and say toroid. All right, here we go. I see a tour right here. High current radio. That sounds like what we want. I'm just scrolling down just to make sure. It looks like there's several pages of inductors, but I have a feeling this one might be where we're looking. Yeah, this looks like, yeah, I think so. Okay, let's just go ahead and search for this guy. Okay, here's an inductance range that looks like would work for us. Let's view that series. All right, DMT series. And prices don't look too bad. And guys, you can click on the sample. So let's just go ahead and see what we can find. There's a DMT3 series. It looks like this is the higher power series. So let's come down here. And I'm looking at the current ranges. We're probably going to have to look at something. See, here's 6 amps here. Now we're starting to drop down a little bit. So it doesn't say it's saturation, it just says 6 amps. So that sounds really close to our 5 amps RMS. So let's just select this guy. And also the inductance, look at this. 299 typical, but it'll drop to 138. And what happens, I'll show you some curves, but I'll explain that here in a minute once we look at the curves of this thing. So here's the part right here. Some more information. DC resistance, DCR, 70 milliohms. Okay. So, you know what? Let's look at the data sheet. We can look at 3D models as well, but let's look at the data sheet. Okay. There we go. Oh, DMT1. This is the data sheet for DMT2. Where's DMT3? It's down here at the bottom. There's DMT3, the higher power guys. So, all right. So here we are, the weight. It's 90 to 100 grams. The size looks like what? Okay, so the L. Let's go look at L for DMT3L. They're going to be all different, but I guess this one here is 138 microhenries to 299. And if we come over here and look at the size, well, they're all same size, 1.85. Okay, that's good. Almost 2 inches around. Yeah, so now we got to go look at some curves, and I think we're looking at this green one. So there's 1 megahertz, so it definitely can operate at, say, 200 kilohertz, which we're talking about is right through here. Black one actually can operate too much higher, right? Okay, we come down here, and here we are. Well, let me see. All right, here we are. It starts off around 300 microhenries, and look at this. As the current goes up, it drops, but it can go up to 10, so that's good, because we're going to have like 8 amp peaks somewhere around there. So we're going to be around here, and the inductance will be under 200. But you know what? At higher currents, we don't need as much inductance, so that's okay. This guy's kind of borderline, but man, yeah, I think this one right here is the 138-6L. I think that looks pretty good. Okay, we're at the bottom of the page. All right, yeah, so I think this 138-6L looks like the one. So, all right, the 138.6. So we can add a couple, 1 or 2, to our samples, and we can say we want samples, and go ahead and start that process.
Hey guys, little commercial break here. A lot of you guys sending comments, really appreciate it. I recognize names throughout the short time I've been here on YouTube, but still not subscribers. So I appreciate subscribing and hitting that thumbs up. That really helps with the YouTube analytics, helps grow the channel, and helps YouTube share my video with other new subscribers or potential new subscribers. So it really does help. Appreciate it, and I try to answer. I'm getting enough comments these days that's kind of hard for me to keep up, but I go to the subscribers first and answer those, and then I answer quite a few of my comments and that. I think you guys know that. So all right, well, thanks a lot, and let's get on with the video. All right, guys, we're moving along. We've chosen 3 important parts of our circuit. Now there's a data sheet with that controller chip, right? And it's going to kind of walk you through that data sheet will walk you through some of the formulas to calculate some of the values, so you guys go ahead and start working on that. Next video, I'll go ahead and come up with some of those values and present that, and we're gonna have to start we're gonna need to start building our schematic, right? And I think we'll use dip trace for that, so we can design our board in dip trace. I might do it in KiCad too. I gotta decide. Maybe I'll do it in both, but that might slow things down, so I don't know. Well, I'll have to look into that, okay? Meanwhile, we're gonna pick out the FET in the next video as well. So I'll probably come up with the values for the control chip in the next video, and the FET, and the output capacitor, and the input capacitor. I think we can choose all those parts. I'll have to see how long the video is going to be with all those parts, because we also had the bridge rectifier, so we might break that up into a couple videos. I'll see how we go. Let me know what you guys think and how things are going for you, what you think of the parts we've chosen, and so on. Okay? All right. Hey, 2 thumbs up to my patrons. Hey, I got another patron since last weekend, so thanks a lot. Appreciate that. That's awesome. And you can become a patron, the link down below. There's also a thank you button down below. It's kind of a new YouTube thing. It's pretty cool, and I've had a few guys give me a thank you, bought me a cup of coffee. Really appreciate that, guys, and thanks so much. I think I'll put your names in the video here, right here. Big thanks to you guys. And the patrons, I got to go back and ask. I know some patrons don't like to have their names out there, and the list changes constantly. I get a couple and then I lose a couple, so I'll have to go back and ask which patrons I can use their names, give them credits too. So thanks a lot. We'll see you next time, and appreciate you guys watching the video.